Okay, so let's start it on 2.5. We're going to take a look at rational functions. Okay, and we've talked about basic rational function that we know right now is if we looked at f of x is equal to 1 over x. This basic one is our base function, and it looks like going down on this side and then going over here. That's going to kind of give us a couple of ideas of certain things. What is the end behavior of this? And then what happens as we get close to 0? Okay, so we're going to look at some more of end behavior type situations with a rational function. There's several different things that we can run into, and we'll cover all of those. Okay. So let's just get started. Apply notation describing infinite behavior of a function. So when it goes infinite, plus infinity to negative infinity. Okay, so what happens, I've got, in general, we're going to kind of use this as a model, but we have got a full rational function where we've got two polynomials. Let's say example, and I'll do a simple one, x squared plus 2x plus 1, and then I've got like x plus 1, x plus 2, x minus 3. If I multiply it out, polynomial. Okay. So what happens if I've got this? Let's kind of do a little shift. I want to take this and do a horizontal transformation, move right by 3, move right by 3. Then my new function would just be that, right? And I move this over, okay? So now out here at x equal to 3, this same thing is kind of happening. Down here, if I drew the line, x equal to 3, that's where I shifted this thing over. That's what I get, okay? Now what it says, this infinite behavior stuff, it says if I start from here and I'm looking for one of these vertical asymptotes, this thing is called a vertical asymptote, by the way. It's a vertical line, this thing blows up. The notation I'm going to use is this x is going to, and now not to a negative infinity or plus infinity, but to 3, and I'm letting you know I'm going from the negative side, the left side. I want to put this little thing right here. As x gets closer to 3, from the negative side, this would be like 2.5. This would be a negative number. The closer we get to 3, it's still a negative number, but now it gets smaller and smaller and it blows up. This is my function. Goes to negative infinity. This thing goes down. So as my little guy is walking toward 3, as he goes here, this thing is blowing up down in the negative direction. Okay. The second one, so this over here is what this is saying. As x approaches c from the left, okay, but will not equal to c, so we can't make this equal to 3 because then we're dividing by 0, okay? This other one is x approaches c from the right. I've got my little guy. He's walking this way to 3 from the positive side, the plus infinity side, f of x. He has to look up to see the graph. F of x goes to plus infinity. Okay. So that's the behavior, the infinite behavior. And then we've got end behavior as well. As x goes to negative infinity, f of x goes to 0 in this case, approaches 0. And then as x goes to plus infinity, f of x again goes to 0, but it goes from the positive side. Okay, so graph this thing. Okay, there's a couple of things that we're going to look at for graphing. Okay. As we go through, we're going to look at the zeros here, and if any time this is equal to 0 from here. So notice that it crosses the axis. It's going to cross the axis where the top polynomial, this is equal to 0. So no matter what this is, so at x is equal to 1, this is 0. 1 minus 3 is -2. -2 into 0 is 0. All of our zeros are going to be based on the top, where the top is equal to 0. Where it blows up, the infinite behavior is around where the bottom is equal to 0. Okay, so this is kind of like the one I did before, and it's just saying from this graph, complete these statements. As x goes to infinity, so the little guy is out here, he's walking this way. As x goes to infinity, f of x is going to, now look, this line is up here. So it looks like 1. F of x goes to 1, not 0 in this case. As x goes to negative infinity, as x goes to negative infinity, we're still getting f of x going to 1. It's just from the bottom side. Okay, and then it's asking you about that infinite behavior. What happens as x goes from 3 from the positive side? F of x goes to plus infinity. As we're coming from this direction, getting closer and closer, this thing blows up, the graph blows up. And then from the left side, as we're walking this thing is starting to blow up, and it's blowing up in a negative direction. Okay, so that's the in behavior, and infinite behavior. Okay, so I'll let you kind of go through those. Let's do this. Let's kind of pick this thing up with a vertical asymptote because we have to get into graphing. The line x equal to c is a vertical asymptote of the graph of the function f. If f of x approaches infinity or negative infinity as x approaches that c. So basically that was in this previous slide. The graph started blowing up around here. This would be a vertical asymptote, a vertical line. Vertical is straight up and down. Okay. So here's some pictures. It just says, I'm going to give you this behavior and kind of graph what this means. So it says here is x is equal to c. This is a vertical asymptote. You're letting it know. And it says as x approaches c from the right, f of x approaches positive infinity. So this says as we go here, it's going to go up. Okay? And then as x approaches c from the left, your f of x goes to negative infinity, and that's given. So that means as we're coming this way, that blows up around there. That's a vertical asymptote, and that's kind of what we're going to, the model that we're going to use to graph based on vertical asymptotes. The vertical asymptotes, so if I've got some function, and this is some polynomial divided by a divisor, vertical asymptotes are where the divisor is equal to 0. And if I've got multiple factors, x minus c1, x minus c2, I would have that many vertical asymptotes. Ever how many factors? I keep writing those as vertical asymptotes. Okay. Now this is saying, what about the situation? Let me do a basic situation. It says that I've got two polynomials, I'm dividing them, and they have no common factors. So let's look at something like x minus 1 over x minus 1 and say what it's talking about. Okay, so it says it has no common factors. If it has a common factor, I want to, let me put x plus 3 here. So I have one common factor. I cancel this out. This is not a vertical asymptote. What happens is this factor, x minus 1 over x minus 1, is equal to 1 except where x is equal to 1. So 1 is not in the domain. So you would graph this piece of it, and wherever x is equal to 1, so I've got a graph, here's x equal to 1. Let me pull this back out. I go through, factor this out, and remember when I'm graphing this thing at x is equal to 1, I put a little circle there. It is not a vertical asymptote. Everywhere else, no matter how small, that's just going to be 1. So this thing is starting to get very close, but at exactly 1, then it's not defined, and we got to pull that out. So that's why this is saying no common factors. Okay. To locate the vertical asymptotes, we just determine the real number is x where the denominator is 0, but the numerator is non-zero. Okay. So we'll build this up. So we want to graph this rational function x minus 3, x squared minus 4x minus 5. Okay. So first of all, I want to factor because I want to remove anything in common, get rid of that, and then I'm going to proceed with analysis. Okay. So this thing is just two factors, the difference being 4 because of the negative. The largest, it's got to be 5 and 1. The difference being 4, that's got to be like that. X squared plus x minus 5x, and then minus 5. Nothing in common. This is the denominator. I set this equal to 0 because I want to see where it blows up. X minus 5, x plus 1. Set that factor equal to 0 and solve. Set that factor equal to 0 and solve. These two, when I graph, are going to be vertical asymptotes. So here at negative 1, I'll go ahead and draw a dashed line. That's my x equal to negative 1. And then over here, wherever that is 5. I'm going to call that 5. I label this line, x is equal to 5. Those are going to be vertical asymptotes, so it's possible I could come here and blow up, come down from here, or here, depending on the nature. These are linear factors, so I'm going to have a kind of an up, down, and then, maybe like here, and then here. But we got to do the rest of the analysis. Okay. We're just going to do the vertical asymptotes and then put in all of the other. We need end behavior, and then some zeros. The zeros are from the top. From the numerator. Okay, and I just solved that. So right around here at x equal to 3, that's a 0. It's going to cross through there. And then I can also do the y-intercept. That's just f of 0. 0, 0, 0, it would be just 3/5. So somewhere around in there, okay? So we need some end behavior to get us started. There's no zeros. So I can't, get across these things. So I'm probably going to be here, here, and then here, or here. And we'll have to look at those. So here's another one, x squared minus 2x minus 3. Just identify the vertical asymptotes. Here looks the very same thing, except I've got different vertical asymptotes. Okay, so I've got another function, x minus 3, x squared minus 2x minus 3. We've done this before. We've just basically removed those numbers that were not in the domain. Remember when we were doing domain problems, we were saying, okay, what's not in the domain? We need to factor difference being 2 of 2 factors. That's got to be 3 and 1. Opposite signs because of the negative. The larger factor goes with this, and then we'd have x squared plus an x minus 3x. That gives us that, and then negative 3 times 1. Okay, so our vertical asymptotes, the things that are not in the domain, is when x minus 3 is equal to 0, x plus 1 is equal to 0, x can't be equal to negative 1. So those are the things that we pull out, and those are vertical asymptotes. That's where it blows up. Okay. Was there anything in common? Aha. We pull that out. This is still can't be equal to 3 because then I've got a 0 over 0, but that's no longer a vertical asymptote. This is the only vertical asymptote. Because we pull it. And if I go down here and if I do my Desmos again, if I can find my Desmos, this, let me pull this out, replace this. Y is equal to, so my x minus 3 divided by, let's go to the original, x squared minus 2x minus 3. And if I graph that, bring this back over, I just see that x is equal to negative 1. So if I plot it, x equal to negative 1. There's that. That's the vertical asymptote. I don't see this over here at 3. And notice I have to be right there at 3 before it shows up as undefined with the circle. It doesn't default that there's a circle there that we would have to remove. And when I draw the graph, I'm going to have to remember that this is not in the domain. This one is not in the domain, but it's not a vertical asymptote because it cancels for all numbers other than 3. Do I have any vertical asymptotes here? X squared, if I looked at that, that's the graph of x squared up by 25, or I'm sorry, yeah, up by 25. This is never, that bottom is never equal to 0. X squared plus 25 has complex roots. So we don't have to worry about that having vertical asymptotes. It won't blow up. Okay. So what about horizontal asymptotes? Okay, so we'll practice that enough. We're going to go back through vertical asymptotes every time. We're also going to do horizontal asymptotes. Horizontal asymptotes, so we did a quick graph. This would be a vertical asymptote, okay, if I did that kind of line. And I usually do it as a dashed line. That's the way it usually shows up. A line like this, so this is like y is equal to 2. This is a horizontal asymptote. That line, we can cross this, but usually it's only going to be for a little bit, and then it's going to go to this line. So here, 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 here. So out in behavior, we could be approaching this line. Okay, instead of blowing up like polynomials, or down, up, down, up, down, those variations that we deal with polynomials. With horizontal asymptotes, if I have with a rational function, we'll be getting closer and closer to those at the end. Okay. So that's the line y is equal to d is a horizontal asymptote of the graph of the function f, and this is a rational function, approaches d, that line, as x approaches infinity or negative infinity. So the end behavior, horizontal just means I'm a flat line horizontal. Okay, I could do other behavior. I may not have an asymptote at all, but I still would have end behavior, and we'll look at those categories of what we've got. Okay. So as x approaches infinity, f of x approaches d. So this would say as we go over here, as x goes to infinity, we're getting closer and closer to this line. We could be from down here and going up. We have to have other information, but all we know is it's either coming here or here. Here we're going this way, and again, we don't have any other information from this. It could be coming from above or coming from there from below, but the closer we get to that line. So we need to be able to say, here's a different things that we're going to run into. Okay, if I'm dividing a polynomial by a polynomial, now this was my standard form, you remember this, a to the n, x to the n, n minus 1, x to the n minus 1, all the way down to my a1x, a0. Here I've got a different polynomial, so I'm going to use a different letter, the b's, but these are going to match the m's, n minus 1 all the way down. And I've got three different situations, and that tells me what's going on, okay? I can get my horizontal asymptotes from these particular things. If n is bigger than m, at the degree of the top is bigger than the degree of the bottom, I have no horizontal asymptote. I've got to divide the bottom into the top to discover the end behavior. I've got to do long division. And sometimes that long division is just impractical. Okay, so we just say there has no horizontal asymptote. If n is less than m, the line y is equal to 0. So this is degree less than this. So this is like a quadratic degree 2, a cubic degree 3. This higher power takes over. This number gets larger and larger faster than this. This thing goes to 0. We have the horizontal asymptote being the x-axis. And if they're the same, basically once we get bigger, it is just determined by these leading coefficients, a to the m divided by b to the m. I just look at this leading coefficients, and it's just that over that. And that line is the horizontal asymptote from this value. Okay. The graph of a rational function may not cross a vertical asymptote. The graph may cross a horizontal asymptote. That is okay. But we don't draw it. We can go solve for some things and do, but we don't really focus on that very much. Okay. So let's take a look at this and see where this graph is coming from. Okay. It says just do the horizontal asymptotes, but I'm going to go through the full setup. Okay. So I wanted to graph. I want to get as much information to graph. Again, there's some things that could go on that we're not going to pick up on, but there's the main thing. Okay. I want to graph this thing, see how close we get to what they've given. Okay. So first off, I can go ahead and do vertical asymptotes. So I want to cancel the stuff out first. I want to see if there's any common. Difference of two squares. This is x minus 3, x plus 3. There's nothing in common, so I don't cancel out. So both of these are going to be vertical asymptotes. X minus 3 is equal to 0. I solve to x equal to 3. X plus 3 equal to 0 and solve x is equal to negative 3. So these two are my vertical asymptotes. Okay. So if I go over here, I look, here's my 3, over here's my negative 3. Those are going to blow up. Okay, so I'm going to put all of these things. These are my vertical asymptotes. Okay. How about horizontal asymptotes? This is what I've got to do. The degree of the top, I just do degree of the top. The degree of the top is equal to 1. The degree of the bottom is equal to 2. The degree of the top is less than the degree of the bottom, so y equal to 0 is that asymptote. If I go back here, this is the top, the n is less than m, here's my line y is equal to 0. This looks like, after we get a long way away, it looks like I can cancel the x's and I've got 3 over x, and we know that that basic 1 over x, 2 over x, 3 over x goes to 0. So y is equal to 0 is a horizontal asymptote in this case. Do I have any x-intercepts? The x-intercepts are from the top. I just set the numerator, denominator, I set the top, the numerator equal to 0. So where's 3x equal to 0? The only places where x is equal to 0. Okay, that's my x-intercept. Set my y, set this equal to 0, and where does it cross? Okay, where is, so these are x-intercepts. What about y-intercept? If there was anything that I could cancel, I cancel, and then I evaluate f of 0. And this is just going to be 3 times 0 over -9. I don't get any extra information out of that. That's just 0. Okay. So from those, I can kind of go back. Let me see if I can get this graphed out from here. So I would have my big graph. Let me get this kind of in the middle. Here, here. I plot my vertical asymptotes. My vertical asymptotes, here's my 3. I'm going to call this 3. So straight line through this. There's my vertical asymptote, and then my -3, about the same distance over. I'm going to call this -3, 3 and -3. I'm going to do my horizontal asymptote. Y is equal to 0 is my horizontal asymptote. Let me slide this over. Sorry, I just labeled that. If I'd had an actual line, I'd have put it dashed over. This one doesn't show up as a dashed line, but that y is equal to 0 is my horizontal asymptote. Okay. My 0, x-intercept, y-intercept just happens to be right there. Okay. So I've got some information. I've got to know that this thing either blows up here, blows up from down there. I don't have any x-intercepts over here, so I can't start and cross. There is no other x-intercept, so I've either got to be here and blow up, or I'll be up here and blow up. Okay, from here, I can do this or this. I have no information, and then here, go down to here, or go down to here, but I'm eventually going to go here. So I would actually have to do a test point in here. One of these is all I need because I know it's not a multiplicity 2 up under here that's going to go. And then I need a test point out here. Okay. So let's say if this was a large negative number as a test point, here's my f of x, 3x, x squared minus 9. If this was a large negative number, so pick something out here, x equal to -100, something big. This would be a negative number. This would be a positive. Negative divided by a positive would be a negative. So this would be negative. I don't cross anything. This would have to go like that. Now let's pick a -1. -1, this would be a negative, that would be a positive number. I don't care what it is. This would have to go through here, here. And if I did +1, positive, divided by that negative, because I'm less than that 3, that would also be negative. And then let's pick something out here. X is equal to 100. I'm just looking at the signs. Positive, positive. This would be positive. So this would come from here and go to there. And let's look at this with that analysis in mind. That's what we're getting here. Okay? That's what we're getting. So we've got to step through all of these pieces and make sure we pick them up, okay, to graph a rational function. Okay. Here's a little different because I had the x squared. I'm still going to have the very same vertical asymptotes. What about the horizontal asymptote? The degree of the top is 2, the degree of the bottom is 2. They're the same degree, so all I have to do is look at the leading coefficients of both of these, 3 over 1. So the line y is equal to 3 is my horizontal asymptote, and I trail off to those in both directions. To get the rest of it, I still have my 0, but I need test points in here to see what am I doing. This turns out to be a negative and a negative around here and then up here. Horizontal asymptotes here. This is a degree of the top is 3, the degree of the bottom is 1. It has no vertical asymptotes. If this thing is just one more, if it's just one more, it turns out to be a straight line. That's called a slant asymptote. I divide the bottom into the top, and then whatever this thing is, that gives me the equation of that line. So let me do the slant asymptote for you version. Okay, so if you ever have that the degree of the top is bigger than the degree of the bottom, in this case 3 and a 2. Top is 3, the bottom is 2. If it's one more, the degree of the top is just one more, then there is a slant asymptote. The slant is a straight line. Okay, and let me show you how you get that, and we're just going to look at this. So I'm going to divide out to get the full version. So I need to divide 3x cubed, and let me finish this out, plus 0x squared plus 0x plus 1, and I'm dividing that by x squared minus 0x minus 9. I want to divide this into this to make it so that I've got something over, you know, the full, and then here, the whole part, and then the fractional part. Okay, so my long division we learn, we start off, we're focusing on the leading term. What can I do? What can I multiply this to x squared to get 3x cubed? I'm missing a power of x and a 3, so I need a 3x. I'm writing it right above this placeholder for the 0x. 3x times x squared is 3x cubed. 3x times 0x is 0x squared. And then 3x times negative 29 is minus 27x. Draw my line, subtract. This is 0. This is plus 27 plus the 0, so now this is 27x. And then I bring down this plus 1. When do I stop? I always stop when the degree of this is less than the degree of that. Well, it is. Okay. So all I had to do was one step. So this thing looks like, if I rewrite this function, 3x cubed, that division part, the function looks like, here's my whole part, 3x, plus my remainder over this. And now, doing that horizontal asymptote of this part, this goes to 0. At x large numbers, this thing, as x goes to plus or minus infinity, this stuff goes to 0. This goes up. And you're only left with this. And if I do 3x, if I do the line 3x, I would say this is the asymptote that it's getting closer to. the end behavior, this is the end behavior of a straight line. Okay. If I had a quadratic here, I would do, okay, well, here's, if it's positive, it's up, up, cubic, down, up, those type things. Okay. But this will dominate. Once I divided it out, this would dominate for large X. Okay, but that degree 1, if it's just one more, this is called a slant asymptote. This is the slant asymptote. The slant implies a linear. Linear. And the only way I get a linear here is if this is just one more than that. Okay, so I paused that. Any questions, Amy, Damien, Marco, Tamika? We're going to be working on that. We're going to step through all of that stuff, doing polynomials and rationals tomorrow.